Hi, this is JLN Murthy, welcoming you to the episode number 2 of Real Numbers, wherein we are going to discuss some of the questions from previous year's question papers, along with solutions and covering the concepts involved. This question appeared in 2019 involving Euclid's division algorithm. So let us see the concept. Euclid's division lemma states that for any two positive integers, a and b, there exist unique integers q and r such that a equal to bq plus r, where r is the remainder, b is the divisor, a the dividend and q quotient. The problem is Euclid's division algorithm to find the HCF of 135 and 225. Solution. Since 225 is greater than 135, we apply the division lemma to 225 and 135. 225 equal to 135 into 1 plus 90. 90 is the remainder, which will become the divisor in the next step. Therefore, 135, the divisor of the previous step, will become the dividend. So 135 equal to again 90 into 1 plus 45, and 90, the new dividend, will be having a divisor 45, the previous remainder. So 90 equal to 45 into 2 plus 0. So good that remainder has become 0. So once the remainder has become 0, HCF will be the last divisor, which is 45. Therefore, HCF of 135 and 225 is 45. Now, we have fundamental theorem of arithmetic, based on which we are going to have some of the problems. Now, question type 1. These are all short questions. Express 156 as a product of its prime factors. So any number can be expressed as a product of prime factors. Let us take up 156 and verify. 156 equal to 2 into 2 into 3 into 13, where 2 is appearing twice, therefore we get 2 square into 3 into 13. So we have expressed as product of prime factors for the given number 156. Second type of question, which came in 2018, you need to find LCM and HCF of two numbers 12 and 18 by prime factorization method. In this prime factorization method, you have to take both the numbers, drill them down to final prime factors products, and out of that you have to choose the least powers covering all the prime factors involved, and if you multiply them, what you get is HCF. And if you take highest powers of the prime factors, wherein all the prime factors are to be included, and taking higher powers of the available prime factors, in this case 2 and 3, powers are 2 square and 3 square, therefore, which results in 36. And HCF is the least powers you have to take, 2 into 3, 6. So what you are getting, HCF is 6 and LCM is 36. Now, question type 3, which appeared in 2019. The numbers are 306 and 657, and HCF of these two numbers is already given to us as 9. Now what to find out then? We need to find LCM. Now we already know that the product of HCF and LCM is equal to the product of the given numbers. So here we have the numbers available, HCF also available, therefore LCM is product of numbers divided by HCF, which is 9, which results in 22,338. Now next, irrationality of numbers, very important concept. This provides a methodology of proving a given number as irrational. The method adopted is contradiction. By contradiction only we can prove this type of problems. What is contradiction? First we will try to state that a given number is rational. Though it is irrational, we call it rational, and the rational principles we will try to apply on that number where it will fail, and the failed process gives an inference that the very assumption of calling the number as rational is wrong, and therefore the given number is irrational. So this is called proving by contradiction. Fine. Now the question is, prove that square root of 5 is irrational. This question appeared 3 times so far, 2017, 18 and 20. It is very important. Not that root 5 is important. Any square root of a non-perfect square may appear in the examination, wherein you have to prove that it is irrational. Okay. Let's look at the steps involved. First, let us assume to the contrary that root 5 is rational. A rational number is always expressed as p by q, where q is not equal to 0, and pq are integers which are co-prime. The very word co-prime means that the given fraction p by q, they are not going to have any common factors other than 1. That is meaning of co-prime. Example, you can take 8 by 9. 8 and 9 both are not prime, but 8 and 9 are co-prime to each other because 8 and 9 don't have any common factors other than 1. Now, second step. You have to square on both sides the above expression root 5 equal to a by b. Then squaring you get 5 equal to a square by b square, or a square is equal to 5b square. So when 5b square equal to a square is divisible by 5. That's the meaning of it. If a square is divisible by 5, then a is also divisible by 5 by our theorem, fundamental theorem of arithmetic. Okay. Now, next step. As a is divisible by 5, I want to call a equal to 5c. For some integer c. Yes. So substituting a equal to 5c in our equation, 5b square equal to a square. A is 5c, a square is 25c square. Now, interesting thing is 5b square equal to 25c square, or b square equal to 5c square. So once again, b square is also having 5 as a factor. Therefore, b also will have 5 as a factor. Earlier we got a as a number having factor 5. Now A and B both are having factors 5, wherein earlier we have declared that A and B are co-prime, where maximum common factor it can have is 1. But now 5 happen to be a common factor, therefore this contradicts our assumption that A and B are co-prime. Therefore the conclusion is our assumption was wrong, hence root 5 is not rational but irrational. This is how we have to conclude. Now the tip is the proof pattern works for proving any irrational number, square root of 2 or 3 or any other square root of non-perfect squares. Now remember to clearly state the contradiction at the end. Yeah, the conclusion is important, wherein you have to give a statement that our assumption was wrong, hence the given number is irrational. With that you have to conclude. Thank you.